You are on air, sir.
Good morning. I would like to share with you some essential steps that we took towards building a quantum computer. My name is Raphael Levin. I am from Jerusalem, Israel, the Hebrew University. Some simple details about me can be found in Wikipedia. There is also a fairly recent, more detailed biography as given. It's easily downloadable. What I am talking about is special reference of how can we use essential features of quantum mechanics, and in particular, quantum sensing and quantum computing, to make a real change, not a quantitative, but a qualitative change, and maybe even things that we didn't think possible by going over to a quantum technology. Now, to what we want is that the capabilities of the computer will increase significantly. Some people talk about reaching quantum supremacy. By this, they mean that one can do things that are impossible to do by a classical computer. I'm not very fond of this because it's not very clear what the criteria is. I rather think about making new computational complexities available. For example, computations which would take forever on a classical machine that can be done in finite time. The canonical example, of course, is factorizing a very large number into its product, which is at the heart of many security systems. If one could do that in a finite time, that would make a large change in our commercial culture. So I would like to see how one can take advantage of features which are essential to quantum mechanics, like parallelism, that I can do several things at the same time, and entanglement, what Mr. Einstein very much did not like. The two particles that can be very far apart still know exactly about one another. And as you know, people all over the world are trying a variety of physical systems to implement such ideas. And almost all of them are using two quantum state systems, which we call a qubit, and are coupling them to one another. This is not what I will do in this talk. I will try to show you how one can get a quadratic increase in the number of logic variables, and even more. I will describe how one can operate at room temperature. As you know, quantum devices nowadays operate almost at absolute zero. I would try to do without the need for extreme cooling. The device needs to be addressed, and it will be done so by lasers, a sequence of laser pulses that are close to one another. I will show how we can do things in parallel, that is, perform several computations at the same time, taking advantage of the essential features of quantum mechanics. I have a technical advantage that one reading is enough. That is, I don't need to read repeatedly in order to avoid quantum dispersion in the results, because there's a price, of course, because I'm reading an ensemble of systems and not a single system. And another practical advantage is that I would be getting an electrical signal out. That is a critical advantage, because then it can talk the device, the quantum device can talk to a classical device. The work that I will be talking about was mostly done in a European project called COPAC. It's a Horizon 2020 project coordinated by Professor Françoise Remarque from Liège, Belgium. And first, I want to explain how do we dare call our device a quantum computer. And this is because an old paper of a famous physicist, Richard Feynman, who said, what I would like to see in the future is a device that I will call a quantum computer, a device that can simulate the dynamics of other quantum systems. And I quote two of our recent papers where we show how our device, indeed, elementary, very trivial, I agree, trivial, but real, how it can simulate the dynamics of completely different quantum systems. How do we do it? A more qualitative description is that we take semiconducting quantum dots. Typically, we operate with dimers of the quantum dots, as shown, colloidal semiconducting quantum dots. We take an array of such systems, and we address the array by a sequence of ultra-short laser pulses. The pulses are very near to one another in time, and they are even very short, so they don't overlap. That the pulses are very short follows by the quantum mechanical uncertainty principle that they have a rather broad width in frequency. And so the first point is that each pulse can excite a coherent set of excited states and not just a single state as is common with a well-defined laser pulse. The second point that I want to emphasize, you can see it on my slide. You probably can see my cursor. There is a time interval big T. Any particular experiment is done for a given value of big T. Variable values of T1 and T3, so the spacing between the first two and between the last and the optical readout are the variables, and big T is fixed. And then I will do a series of big T computations. Each big T gives me another logic. We show here a simple situation of free laser pulses. We are trying to do more. 4 is already possible, 6 is what we are aiming at. Some of you may be experts, and for the experts, I have this slide. Please excuse me that it's a technical slide, but I'm talking to the experts. In A, we see a series of the free laser pulses. They are about 0.3 millisecond apart. The free pulses come together. They are very short and very shortly separated in time from one another, and then the experiment is repeated every 0.3 milliseconds for about 1,000 times. What we show is that we control each one of the individual pulses. We assign to it a phase at our discretion, so the phase can be varied. We then read the system in this particular slide already electrically. What is the advantage of an electrical reading? Quite apart from the technical advantage, it is that the array of quantum dots acts like the Bragg diffraction, where are fluorescent signals coming in different space directions. And by electrical reading, I don't need to go to different directions in space to read the output. I read all directions simultaneously. Very important to me is the lower right-hand corner, where I show typical output, what we get out of each particular experiment. Each big T gives us a set of different maps. A map is shown, two maps are shown. One is shown corresponding to an echo direction. The signal comes out in the direction of the incoming, and also in a non-echo direction. It is shown as a function of the two delay times that I drew your attention to, and it shows the essential quantum nature of the situation. Why? Because along the diagonal of such a picture is the population of a different excited state. That's a classical situation. Everything that is off diagonal is coherence, is quantum, and we are able not to read just along the diagonal, but to read the entire square. That is, we have a quadratic increase in capabilities. If I want to describe it in words, the logic variables that we use are the populations of the different states that we excite, and this is the key point, the coherences between the different states. Because we excite states coherently, we can measure the coherence between the different states, which means that rather than n classical readings, we have n square readings. The fact that we use a sequence of pulses within a given experiment means that we excite also states of dots that are not necessarily coupled to the ground state, so we have the entire map at our disposal. I would like again to make a technical point. Our observables would be written in a Dirac notation in the way that I've drawn. I like to call these states Gelfand basis states. Israel Gelfand was a distinguished Soviet mathematician, as you must all know, and they close a Lie algebra, which is important for me as a technical advantage. And as I already emphasized, we measure at different values of a big delay time t, and so we have extensive output. Let me show you a simple example. I am going to simulate the vibrational dynamics of a triatomic molecule. So I'm simulating vibrations from the dynamics of the electronic states of my quantum dots. So it is quite different. And we show on the left the first and second excited states of the dots. But actually, these are many quantum states lumped together that on the crude drawing, on the first drawing on the left, they are not resolved. But these are cadmium selenide quantum dots, and so there is a strong spin orbit coupling, and these states are resolved in the way that I'm shown. They still, if I will use a dimer, which I am very much in favor of, there is Coulombic interaction between the two dots of a dimer, and these states will be further split. So 64 states in all can be read. At the moment, we use 8, which is already, please H² variables. And I show you here a very simple example how the coherence between the lowest excited state and the highest excited state of S1 gives me one kind of reading. So it's one set of coherence, and the other coherence between lowest state of S2 and highest state of S1 gives me another coherence, which, because the spacing is shorter, will be slower, and the variables that I'm going to read in this manner are the energy transfer between the two bonds of a triatomic molecule, and also the bond distance, a purely quantum output. And here is actual what I can do. So the top set is for reading the energy transfer between the two bonds. Is the reading at different values of big T of the coherence, and you see tiny portions of the map. These are not the entire maps. It's just a small corner of the map showing the coherence that I'm looking at different values of big T, which enables me to read the energy transfer. And if I take a rather different situation on the map, I move to the same maps, but to a different place, then I get the bond distance that oscillates with time. Okay. You can ask, can you explain what you're doing? And one way of thinking about what we are doing is to go back to a paper of Dirac, Paul Dirac, one of the fathers of quantum mechanics, who has shown that one can mimic, not physically the same, just mimic a quantum state. A single quantum state can be mimicked as a classical oscillator. And so we can think of, in order to understand what we are doing, we can think of our system as a set of big N coupled classical oscillators, and the lasers simply change the energy of these fictitious oscillators. And so we have, if you want, an analog quantum computer. Okay, noise. It seems that noise is a universal feature of quantum devices. It's a plague of everybody, and we also get our share. What is the major source of noise for us? It is that we are using semiconducting quantum dots, colloidal semiconducting quantum dots, and they are not stoichiometric. They do not all have exactly the same number of cadmium or selenium atoms. And here I am showing you the situation in a typical dimer where there is size fluctuations in the diameter of both the small and the large dot of the dimer. And because of these fluctuations, of course, the energy levels of the dots are not quite exactly the same. There is fluctuations in the energy levels. Because the energy depends on the size in a manner that you're familiar with, say from a square well problems, but the dependency is not strong because the size does not vary too much. The Gaussian dependence on the size is also a Gaussian dependence on the energy levels. And as we have shown in the reference given, as long as the size fluctuations is less than about 5%, we can still reliably operate because the decoherence that is caused by the size fluctuations is manageable on our time scale, which is about 100 femtosecond. That's the duration that we need. I mean, 200 femtosecond on a good day, but that's enough for us. We don't need anymore. The fluctuations that are induced by vibrations, the solvent, whatever, are too slow to matter on the kind of time scale that we're talking about. So it's the size fluctuations that is the determining factor. Okay, what's the future for us? We want to engage more logic variables. We can do this by reaching higher excited states of the dots. Already, we know that's already possible. And as I emphasize, we want to measure several phase matching directions simultaneously. Also, because of size fluctuations, there are fluctuations in the coherences. If we can measure the fluctuations in the coherences, we will have n to the power 4 logic variables and not n to the power 2, a very major increase yet to be done. Last but not least, to do things exactly, we need a closed Lie algebra. But one doesn't, in practice, one doesn't really need the algebra to be closed. One can use so-called surprisal analysis, something that we are rather pleased about in Jerusalem. One can use surprisal analysis to identify the important observables and not all the observables. In Jerusalem, when we part from one another, we often, typically, we will say shalom, which means peace. And so I thank you for your attention, and I say to you shalom from Jerusalem.
транспортно-логистический холдинг «Российские железные дороги». Мы развиваем транспортную инфраструктуру страны, строим новые станции, вокзалы и создаем новые возможности для вашего бизнеса. Лучшие скоростные и высокоскоростные поезда сделают ваше путешествие комфортным и безопасным. Мы – локомотив экономики. Сотни миллионов тонн грузов ежегодно. Развитие науки и социальной сферы – это наш вклад в благосостояние страны и ваша уверенность в завтрашнем дне.
Я новая Hyundai Creta. Hyundai.
Есть история фантастическая. Есть история сказочная. Есть страшная история. А есть история реальная. Юка всегда реальная история и диагностика автомобилей с пробегом. Юка – официальный сервис Hyundai. Смотрите историю и диагностику автомобиля и покупайте.